Hello everybody, I hope you're doing well. Welcome to another video reviewing your probability and statistics fundamentals. It's so great to be with you guys today on a Wednesday morning. So today in this video, we're going to be continuing our discussion on hypothesis testing, but we're going to be talking about proportions. So the concept of hypothesis testing still remains the same from what we discussed in the previous video, but we're just going to be talking about sampling distributions of proportions. So if you don't really understand sampling distribution of proportions, I'd highly recommend watching the relevant video on that where I go through the formula for the standard deviation for a sampling distribution of proportions and also the mean of a sampling distribution of proportions. So just as a recap for population proportions, when we have a sampling distribution of population proportions, we know that like the mean is going to be like p basically, so it's going to be like your p hat, and we know that the standard deviation, so s sub p hat is going to be equal to the square root of p hat 1 minus p hat over n. And now using like this logic, right, we're able to essentially build our formula for calculating the z or t statistic when we need to. And we did this in the confidence interval video, so I would also recommend reviewing that video if you forgot or want a quick refresher. So we're going to be continuing our discussion of hypothesis testing, and these are the three types of hypothesis testing we need to know. So the first two tests, where you have an alternative hypothesis where the proportion is greater than p naught or p is less than p naught, where p naught is the null hypothesis proportion, those are going to be your one-tailed scenarios. So these will be one-tailed. And this case where you have an alternative hypothesis where the actual proportion is not equal to our null hypothesis proportion, this is our two-tailed scenario. So we have two types of tests when we do hypothesis testing. We have two-tailed and one-tailed, and this is the formula we use to calculate the z-score, which we will use to find our p-value, and the z-statistic or the t-statistic, depending on if the normality checks pass or not, can be used to test your hypothesis. So I guess we could just jump real quick into the examples because I think you'll understand a lot better. So in example 1, suppose that in 2015, the proportion of teens who use TikTok in your university is 60%. The year is now 2016, and you want to find the proportion of students in your university who use TikTok in 2016. You sample 400 students from your university and find that 250 out of the 400 use TikTok. So you think that the proportion of teens who use TikTok is higher due to recent social media trends. So we want to use a significance level of 0.05 and conduct a hypothesis test on our claim. So let's unpack what we have here, right? So we know our sample proportion p hat equals 250 over 400 because we have sampled 250 out of 400, right? And we find that 250 out of the 400 use TikTok. So we're going to need to know that. We're also going to need to know that our old proportion, right, is going to be 0.6. And we also know that the alpha, the significance level, is going to be 0.05. So let's come up with the hypothesis test. So we start with the null hypothesis. So our null hypothesis H naught. Well, we know that in 2015, the proportion of students who use TikTok is 60%. And our null hypothesis in this case would be in 2016, the amount of students in your university who use TikTok is going to be the same as the proportion in 2015. So we're going to say that P, or the true proportion, is going to be equal to 0.6 because we want to signify that there is no difference from 2015 to 2016, right? So now we have the null hypothesis. We want to have the alternative hypothesis. What do we claim in our problem? We claim that that we think that the proportion of teenagers, or I meant students, sorry, who use TikTok is higher due to recent trends, right? So we might say that our actual proportion is greater than 0.6. So what happens here? Our alternative hypothesis is the proportion is greater than a number. So we're only focusing on one side. This is a one-tailed hypothesis test, right? This is going to be important for when we calculate our p-value, right? And alpha will come in handy at that point. Okay, what else do we need to know? We need to do our normality check, right? So if you recall from sampling distribution of proportions, we have to check that np hat is greater than or equal to 10 and n times 1 minus p hat is greater than or equal to 10, right? So what is n in this case? N is 400, right? And what is the sample proportion? It's going to be 0.6, right? And why we're using 0.6, we're centering our distribution around the null hypothesis. So we have to use this proportion when we're doing our normality check, right? Because we center our sampling distribution around our null hypothesis because we initially assumed the baseline to be the case. So this is going to be obviously like 240, which is definitely bigger than 10. We also can check that 400 times 0.4 equals 160, which is greater than or equal to 10. So we can use the z distribution, right? Because normality checks pass. And if I made a typo in my previous video where I used this p hat to find the normality check, please disregard that. You want to essentially use the null hypothesis proportion as the quote-unquote p hat for the normality check because we're centering our distribution around the fact that our baseline is the case. So we want to use the appropriate center to check for normality, right? But nonetheless, we're going to use the z distribution. So we want to find the probability of getting a sample proportion above 0.6, right? So we have to convert that into a z-score, right? So our z-score in this case would be 250 over 400, right? Hold on. So 250 over 400, right? Minus, what is the p? Well, the p is actually 0.6 because that's our center for this sampling distribution of proportions, right? This is our p hat, essentially, this fraction. Okay, now in our denominator, we need to figure out like the standard error, or I guess the standard deviation is this distribution, right? So in our standard deviation for proportions, what you want to do is you want to use this center, right? Because this is the spread of our sampling distribution and proportions, right? We assume the center to be at 0.6. So we have to use 0.6 when we're calculating our standard deviation, right? So you use the formula like square root of p, 1 minus p over n. And the reason why we're using 0.6 as our p is because we're assuming that our null hypothesis is the case. So we center our distribution where the mean is 0.6 and our standard deviation is using this 0.6. So we use this formula to calculate our standard deviation. So with that being said, we get our z-score, right? And when we get our z-score, let's take a moment to punch this into our calculator. So when I do that, I get the following. And oh, by the way, the sample size is 400. So we're going to use 400 right here. So the z-score I get is 0.83. So I want to use my z-table and find the probability of getting a z-score above 0.83. So this is equal to 1 minus the probability of getting a z-score smaller than 0.83. And now I can find this value in my table. So when I go to z-table, this area here we want to find, and this z will be 0.83. So if we go to 0.83, I will see that I get this gray area value as 0.79673. So we want to do 1 minus 0.79673, which is approximately this 0.20307. Okay, so what did we find here? We found that the probability of getting a observation that is more extreme than 250 out of 400, right? Getting a sample proportion that is much larger than, 250 on 400, right? Is this scenario, right? We get a p-value that is the p-value is approximately 0.20307. But what do we know? This value is much larger than 0.05, right? So what does this mean, right? Well, because we have a p-value, or the chance of getting a observation more extreme than this, right, is 0.20307. So approximately a 20% chance of getting a z-score that is above 0.83, or getting an observation that is more drastic, right? So the fact that 0.20 is greater than 0.05 means that the observation we're getting, or our sample proportion, is not really surprising, right? So we actually fail to reject the null hypothesis. We don't really have much evidence, or enough evidence, to conclude that the observation we get is statistically significant from our null hypothesis of 0.6, which would lead us to believe that the true proportion of students in my university who use TikTok is not zero point 0.6, right, or above 0.6. So we fail to reject the null hypothesis for now, right? But unless we get a sample where we get a very drastic difference between the sample proportion versus our null hypothesis expectation, we really don't have much evidence to conclude in favor of the alternative. And that's because this p-value of 0.20307 is above 0.05, so don't have enough evidence. So that clears up example 1. All right, let's do example 2. So example 2, this is a little bit long. So your AP exam for AP Statistics is coming up. If that's actually the case, good luck on your AP exam. I know you guys will do great. You want to estimate the percentage of students who prepared for the exam. And we assume that students are generally honest with other students/friends. And you read about the rate at which students have been getting 5s from past years. And in a past session of the AP Statistics AP exam, 16.2% of students have gotten a 5. So we'll assume that nationally, 16.2% of students prepared for the exam. For the sake of simplicity, right? It's a simplifying assumption. So I sample 100 students in my school who are about to take the exam and find that 20 of them prepared, right, or said that they prepared for the exam. Is my sample proportion, i.e., the 20 out of 100 students who say they prepared for the exam, significantly different from the national proportion, i.e., the 16.2% of students who have gotten a 5? We'll conduct a hypothesis test at the significance level of 0.05. So, in other words, 95% confidence, but we'll use significance level of 0.05 to be consistent. So, what do we know from this problem, right? We know that the national statistic, right, of students who prepare for the exam is 16.2%. We also know that our sample proportion, p hat, is 20 out of 100. We also know that our sample size is 100. We also know that the alpha we're going to use is 0.05. Let me double check. Yep, see 20 out of 100 from our sample, say they prepare for the exam, and we're going to use 0.05 as our significance level. Okay, so now that we have our alpha, let's write our hypothesis S. So we need the H naught, right? So we say that in this case, our null hypothesis, or our baseline assumption, is that the sample proportion is actually 16.2%. So i.e., it is plausible that as a baseline, 16.2% of students actually prepared for the AP exam. So we're going to say P equals 0.162. Now, what's the alternative hypothesis? We want to see if our sample proportion really makes sense in the context in a world where 16.2% actually do prepare for the exam, right? So we want to see, is that national proportion of 16.2% a far-fetched assumption, right? We want to see, is our sample proportion significantly different from the national proportion? And when I mean different, we are not talking about, oh, our sample proportion is bigger or it's smaller. We're just saying different, period, right? So our alternative hypothesis is the true proportion is not equal to 0.162, right? So what kind of test is this? We're working in this type of problem right here, right? Where H naught is the true proportion is not equal to our null hypothesis proportion of P naught. So what do we have here? We have a two-tailed scenario. So we have a two-tailed scenario, right? And I'm going to show you how the two-tailed scenario differs. And the difference will lie in how we're getting our p-value and where our conclusion will be made. But let's actually go through the process, though. So one thing to understand about two-tailed is we want the chance of a sample proportion being more extreme, right? We want the chance of an extreme observation, right? But if we have this distribution where we center around p naught, right, and this happens to be my sample proportion, right? Getting the sample proportion that is more extreme than p hat would be getting this probability, right? But we care about having a significant difference, right? We want this distance to be as big as possible, right? For the difference to be as significant, right? So we also have to consider the symmetric nature of the distribution, right? Where this guy here will be, p hat minus p naught, right? So it'll be like, you know, yeah. So it'll be like, yeah. So it'll be like, some other sample proportion, right? So we'll call it p hat one, right? And basically, like in our world, right, this distance in green and this distance here in green will be the same. So getting a sample proportion that is more extreme than p hat is equivalent to getting this probability, but also this probability, right? Because we want a significant difference between whatever sample proportion I get and this p naught, which is the null hypothesis proportion, in a world where we assume that the null hypothesis is true, right? So we actually want like these two probabilities to sum up, right, to the significance level of 0.05, right? But because like these areas here are symmetric in a world, in the case of potential normality assumptions, um, what we can say is that this green area right here, one of these green areas is going to be 0.05 divided by 2, right? Because we're talking about a two-tailed scenario, right? Now let's talk about how we're going to use that. But first, we need to do normality check, right? So what we want to check is we want to check that NP is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, right? And the way we do that is we know our sample size is 100. We know our p is going to be 0.162. So this is going to be 16.2, which is definitely greater than or equal to 10. We also can say that this is equivalent to 100. 1 minus 0.162, which equals 100 times 0.838, which equals 83.8, which is definitely greater than or equal to 10, right? So we know that normality check passes, right? So normality check passes. So what does that mean? We can use the z distribution, right? So we want to find what is the z-score associated with this sample proportion of p hat, right? So I'm going to find the z-score. So z is equal to 20 out of 100 minus 0.162, because that's the center of our sampling distribution of proportions. What will the standard deviation be? Well, we know that our center is centered around 0.162 because we're assuming that the null hypothesis is true in this world. So our standard deviation will be 0.162 times 1 minus 0.162 over 100, right? And what does this z-score equal? It's going to equal the following. So let's punch this into our calculator. So it turns out our z-score is 1.03. So if we go back to our drawing, right, and we plot this normal distribution, right, we know it's centered at 0, and 1.03 is here, and we also have negative 1.03 here. So to get a sample proportion that is more extreme than this 20 out of 100 students we sampled, we want this probability, but we also can get this probability, right? Because any z-score that lies in this green region is still representing a potentially significant difference, right? And also in this region, the same story holds, right? So what we can do is we want to find, like, we want to see if the sum of this green probability and this green area right here, like these two green areas, is under 0.05, right? But because this area right here is symmetric, all we have to do is just find that we have to check the probability of z greater than or equal to 1.03, which will be equal to the probability of getting z less than or equal to negative 1.03. And this is due to the symmetric nature of the normal distribution. So we can essentially go and look in our table, look for the z-score of negative 1.03, right? And that will be 0.15151, right? So basically, our p-value, right, is 0.15151. But our new alpha that we're going to be worrying about is 0.05 divided by 2, right? And this is due to the fact that we've said that the sum of this area and this area must be 0.05. But if this area equals this area, right, then you know that this green area is going to be 0.05 divided by 2, right? So all we have to do is check 0.15151 is less than or equal to 0.025. And it just so happens that this inequality is not true. So again, we fail to reject the null, right? We don't really have enough evidence from our sample to conclude that our null hypothesis of 16.2% of students preparing for the AP Stat exam is more than far-fetched, right? So we fail to reject the null hypothesis, and we would just have to take another sample and run the test again, and maybe even take a bigger sample, and maybe that might help reduce the spread and hopefully get your probability to where you want it to be, right? Or get your p-value to where you want it to be. So again, we fail to reject the null hypothesis, and this is the case of how you handle a two-tailed scenario. Again, like my tip for doing these hypothesis tests are to write out everything you're given and go step by step in the formula, right? Like get your z or t statistic, draw the distribution, and figure out what area you want to get. Once you know what area you want to get, i.e. like through coloring the area that you want in your drawing, use the z table or the t table to get the value you need. And using that, you can estimate your p-value and compare against the threshold. And if you're below the threshold, your p-value is below the threshold, you can actually reject the null hypothesis. And you have some certainty to believe that your null hypothesis seems very far-fetched. But if your p-value is above the threshold, you fail to reject the null hypothesis, in that you don't have enough evidence to conclude a statistically significant difference between your observation and the null hypothesis. So that'll wrap up hypothesis testing. Hopefully this video helps to give a refresher on how to do hypothesis testing for sampling distribution of proportions. Till next time, hopefully you have a good rest of your day, and looking forward to seeing you in the next video.